Hello, welcome back to the NPTEL online certification course on deep learning. So, for last few classes, we are discussing about the generative network, where what we have discussed is that if you feed in a latent vector or latent variable to the generative network, then the generative network will give you an output data or reconstructed image or the reconstructed object. And the kind of generative network that we are discussing so far is what is known as adversarial autoencoder. So, we have started our discussion on adversarial autoencoder. We have discussed about what is variational inference. Today, what we are going to discuss about how do you practically realize a variational autoencoder. Then we will briefly discuss about another generative model, which is known as generative adversarial network, and we shall conclude our lecture or conclude this course with the applications of generative adversarial network. So, this is what we have discussed in the previous lectures, that our initial objective was to minimize the KL divergence QZX PZX, and we have seen earlier that this is same as maximizing the QZX log of PXZ, QZ given X log of PXZ, where PXZ is the joint distribution upon Q of Z given X. And we have seen that this is what is known as variational lower bound, and the concept of variational lower bound that came because we have seen that P of X, computation of P of X was intractable. So, what we tried to find out, and we have seen that this particular expression, the variational lower bound, gives a lower bound of P of X. So, in order to maximize P of X, it is equivalent to maximization of the variational lower bound, because when we know that this variational lower bound is always less than P of X. So, if I can maximize this variational lower bound, P of X is also going to be maximized. So, this is an indirect way of increasing the probability distribution P of X. So, our aim was now to maximize this variational lower bound, and this variational lower bound can be rewritten as sum of P of Z given X log of P of X given Z into P of Z upon Q of Z given X. So, this expression can be rewritten as sum of Q of Z given X log of P of X given Z plus sum of Q of Z given X log of P Z upon Q of Z given X. So, here you find that the second term, that is sum of Q Z given X log of P Z upon Q Z given X. This is again another KL divergence between P of Q Z, KL divergence between Q of Z given X and P of Z. So, this can be simply written as the first term is now expectation value of log of X P X given Z, and you find that this log of P X given Z is nothing but log likelihood. And when you try to maximize this, basically the first term maximization of this means you are going for maximum likelihood estimation, and the second term, which is the minus scale divergence of Q Z given X P Z, maximization of this term effectively means that you want to minimize the KL divergence between Q of Z given X and P of Z X and P of Z. So, then we have seen that how we can translate this loss function or maximization of the loss function into an autoencoder architecture. So, for that again we have gone back to our graphical model, that given your latent variable or latent vector Z and the data which is to be reconstructed X. So, there is a probability involved, probability density distribution involved, that P of X given Z, that is given Z, I want to maximize what is the likelihood P of X given Z. And similarly, to get your latent variables or latent vectors from the training data, I have another probability distribution involved, which is Q of z given x. So, in terms of network realization, you realize both P and Q with the neural networks, and the network model that you get is something like this, that Q of z given x is your encoder network, P of x given z is the decoder or the generator network, and Q of z given x actually gives you the latent variable, which is z. So, here comes the difference between the traditional autoencoder and the variational autoencoder. In case of traditional autoencoder, the latent vector z was deterministic, but with this variational autoencoder, because we have a term P of z, that is the probability distribution of the latent variable z. So, instead of getting a deterministic latent variable as in case of autoencoder, over here what we expect is the encoder part will give us a probability distribution or the parameters of the probability distribution of P of z. So, it is therefore expected that z codes, the z latent variable that we get, that should match with the distribution of P of z, and we assume a normal distribution, a prior of normal distribution for P of z, where this normal distribution is 0 mean and unit variance. So, that will be a prior for P of z. So, as you have seen that here, instead of getting a fixed latent variable z, what you are getting is a distribution of the parameters of the distribution. And this is the network realization that we have, the encoder network on the left and the decoder network on the right. In between, what you have is, as the encoder is giving you the distribution of z, I can sample a z from that distribution and feed it to the decoder of the generator network, and the decoder of the generator will give me the generated or the reconstructed data, that is x. And then we have discussed about the problem involved in this sampling, which makes it difficult for the backpropagation learning, because gradient cannot flow through the sampling process. So, in order to avoid this problem, we have made use of the reparameterization trick. So, this is what we have discussed in details in our previous lecture. So, now the problem is that we are trying to maximize the expectation value of log P of x given z minus KL divergence between Q of z given x and P z. So, maximization of this expression means we are trying to maximize expectation value of log of P x given z, and we want to minimize the KL divergence Q z given x P z. So, we have both this maximization and minimization involved. And for this maximization, you find that the maximization of expectation value of P of x given z is nothing but a maximum likelihood estimation, which we have encountered a number of times in our discriminative network. So, this can be solved using any of the classifier, or the input is z and the output is x. Then you optimize the objective function by using different techniques, for example, log loss or regression loss and all that. Whereas, for minimization of the other part, that is the KL divergence, as we said that we assume a prior distribution of P of z, which is normal distribution with 0 mean and unit variance for all the attributes of the vector z. So, by when we try to minimize the KL divergence, that effectively means that we are pushing the parameters of Q z given x towards that normal distribution of 0 mean and unit variance. So, by using this prior, this normal prior, it is advantageous in two ways. Firstly, it becomes very easy to sample latent vectors from this normal distribution, and secondly, assuming that Q of z given x to be Gaussian distribution with parameters mean and the covariance matrix sigma, it allows this KL distribution to be in a closed form, and that becomes easy for optimization. So, this closed form representation is something like this, that this KL distribution can now be represented as 0.5 into trace of the covariance matrix sigma plus the vector mu transpose mu minus k minus log of determinant of the covariance matrix, where this k is actually the dimensionality of the latent code or the latent vector z. And this can be further simplified as all of this. I will come to the final expression. So, this finally comes down to 0.5 into sum over k sigma x k plus mu x k square plus 1 plus log of sigma x k. So, this is the final closed form expression for that loss function that we get, or the KL divergence form that we get. And this is the advantage of assuming normal distribution prior for q of z given x. But in practice, we predict log of sigma x instead of sigma x, since it is numerically better to exponentiate a value during runtime rather than taking a log operation. So, your final expression then becomes the KL divergence of q of x given z and the normal distribution 0, 1, that is equal to 0.5 into, so instead of sigma x k, now it becomes exponential of sigma x k plus mu x k square plus 1 plus log of sum of x k. You find that this log of sum of x k has come from the product term, which is basically determinant of the covariance matrix sigma. Right. So, this is log, not sum of x k, but log of the different components of the covariance matrix sigma x k. Right. So, now let us see that what are different kind of output that we can have using this variational autoencoder. So, this gives the reconstructed output from the variational autoencoder. For given inputs, you have the different reconstructions, and this second set of results is showing that if I sample a vector from a normal distribution, 0 mean unit variance, then the generator network generates or reconstructs the signal as given in the last one, in the last row. So, you find that in many cases, this the generated samples or the generated data that closely resemble the MNIST database, the characters which are available in the MNIST database. This is again another set of output, again reconstructed from this generative model, the variational autoencoder, which is trained on Celib, a database. With variational autoencoder, we can have another trick following the vector arithmetic approach. That is, if we take a set of face images with glasses and the corresponding latent code we say is C1, then take another set of face images which are without glasses, the corresponding latent code is C2, then C3, the vector C3, which is C1 minus C2, that gives you the code for the glasses. Now, if we have a face image without glass, we can impose this glass onto that face image. So, you take a new face image without glass and its corresponding latent code is C4, then you generate a latent code which is C3 plus C4. So, you find that C3 was the latent code for the glass and C4 is the latent code of a face without glass. So, when we are making C3 plus C4, effectively I am generating a latent code for a face with a glass. So, this transition is possible because the latent space is continuous instead of clusters of points that you get in case of traditional autoencoder. So, a set of results on this. So, it says that we had a set of images with glass, and we also have a set of images of man without glass. You subtract these two, you get the latent code of the glass. Then you have set of images of women which are without glasses. Then you add the latent code of the glass with latent code of women, and then you feed this latent code, the latent vector, to the generator network, and the generator network outputs faces of women with glasses. So, this is a nice trick where we can play with the latent codes in the latent space, and I can generate the output data in various combinations. So, that was our variational autoencoder. Now, briefly I am going to discuss about what is generative adversarial network. So, generative adversarial network is another form of generative model for reconstruction of the data from the latent code. So, unlike in case of variational autoencoder, where the distribution, the probability distribution of the latent code was quite explicit, in case of generative model, this implicitly defines the probability distribution. So, a sample code vector Z from a sample, you sample a code vector Z from a simple and fixed distribution, which may be say normal or uniform distribution, feed it to the generator network, which is trained as a differentiable network, and this generator network then map X to your data, maps this latent variable Z to the data point X. So, effectively what you have is, you have the data from a true data distribution, and the generator model, what it does is, it takes a sample from some distribution, maybe say unit Gaussian distribution, and this then it generates another distribution of data, which is the p hat x. Then while training this generative model, what we want to do is, we want to minimize the KL divergence between p hat of x and p of x. P of x was the true distribution of the data, and p hat x is the distribution of the generated data. So, we want to minimize the KL divergence, and while minimization of that, you try to update the parameters of the generative model, so that effectively or eventually your p hat x becomes similar to p of x. So, as we have shown that the blue region in the previous diagram, that was your probability distribution of the real image, whereas the black dots, that was actual images from the true distribution, actual images, samples from the true distribution p of x. Generative model, for which the parameters are theta, this gives you a distribution which is p of x, p hat of x. Then this was generated by taking points from, sampling points from an unique, from say a Gaussian distribution, and then theta is optimized by minimizing KL divergence between p x and p hat x, and eventually the green distribution, initially that starts randomly, and then gradually it aligns to the blue distribution, as was shown over here. So, the green distribution is the distribution of the generated data, and the blue distribution is the distribution of the real data. So, initially green distribution starts at random, and while the training goes on, this green distribution eventually becomes similar to the blue distribution. So, this is how the generative model works. So, in generative adversarial network, which is popularly known as GAN, the main idea is to have two neural networks, and they will compete with each other. So, effectively it is a game theoretic approach. One of the neural network is a generator that samples Z vector from the latent space and tries to produce a realistic sample. And the discriminator network, which is a competitor of the generator network or adversary to the generator network, that is why it is adversarial network. So, the discriminator network, it tries to distinguish between the fake samples, which are actually coming from the generator, and the real samples, which are fed to the discriminator, to discriminate between the real samples and the generated samples, now called as fake samples, which are generated by the generator. So, while this contest goes on, eventually both the generator and the discriminator, both of them learns the distribution, and this is implicit, it is not explicit, unlike in case of variational autoencoder. So, this is what is our network. In fact, let us assume that dx represents the probability of belonging to real class for a given sample x. So, the discriminator will try to decrease dx for real samples, will try to increase dx for real samples, because it wants to discriminate between the real samples and the fake samples or the generated samples. So, x being input to the discriminator network, if this x comes from a real sample, the discriminator will try to increase d of x, that is its probability distribution. Whereas, if this x is a fake sample which comes from the generator network, then the discriminator will try to reduce d of x. In turn, generator will try to increase d of x for its own generated samples, and that is how they are locked in a game. So, by doing this, now there are two training components. One of the training component is training of the discriminator, and the other training component is training of the generator. So, for training we need the cost function. So, for training of the discriminator, as we said, the discriminator wants to maximize the probability for the real data, and it minimizes the probability for the generated data, or effectively it maximizes the probability or log likelihood of 1 minus d of g z, where g z is the data generated by the generator network from the latent variable which is z. So, while training the discriminator, it is a maximization operation where it is maximization over the log likelihood log of dx plus the value of estimation value of log of 1 minus d of z. So, maximization of this will train the discriminator. On the other hand, the second component, which is training of the generator, obviously the generator wants to maximize the probability of its own data, which is generated by the generator itself. So, it tries to maximize log of dgz, or expectation value of log of dgz. So, you find that these two are in opposite direction. The discriminator tries to minimize dgz, probability of the probability distribution of the generated data. On the other hand, the generator tries to maximize log of dgz. So, they are actually working in the opposite direction. In effect, what is done is the generator is trying to fool the discriminator, so that discriminator cannot discriminate between which is the real image and which is the fake image. And while doing so, both of them learns the distributions. So, this is just what is shown as the algorithm, how the generator and the discriminator networks are trained. So, given a set of noise samples or the latent variables z, the generator network generates a number of data samples. Using these data samples, the discriminator tries to maximize the same cost function, which is log of dx plus log of 1 minus dg of z. And once the discriminator is learned, it stabilizes, then you come to the training of the generator, wherein you try to maximize d of gz. Okay. So, these two training operations occur one after another, effectively making both the generator and the discriminator quite strong. So, this GAN has been applied in many application domains. There was a paper in ICLR in 2018, where this generative adversarial network was used for synthesis of high resolution images. So, this particular slide shows two images which are synthesized, and you find that though the images are synthesized, but they are really looking like real images, right. So, that shows what is the power of generative adversarial network. It has also been used for image to image translation. So, this is a CVPR paper in 2017, where you find that given the semantic segmentation of a scene, using the generative adversarial network, it is possible to generate or possible to synthesize real looking images. Similarly, from the input levels, you can also generate real looking images. Given black and white image or grayscale images, you can generate color images. So, all these are possible using this generative adversarial network. This shows another one, that if we have a sequence of input frames which are basically semantic segmentation of different frames, then it is possible to generate a real looking video in different style. Again, for that we have to train the generator network and the adversarial network in a proper way. This is a piece of work which is for image inpainting. Image inpainting is a problem where if you have an input image where there are a large areas where the information is not available or the image is damaged. So, we can try to fill up those damaged regions using the information of the overall image. So, this generative adversarial network has become very effective in that area also. So, for that what you do is you use a generative network which is pre-trained over the domain of images for which we want this inpainting operation to be active. And then use this generator network to generate a real looking image. And then our aim is that when we compute the cost function will have two components. One is the perceptual component, where the discriminator tries to discriminate between this generated image or the fake image and the real image. That means how realistic this generated image is. So, that gives you a perceptual loss. And another loss component which is contextual loss. The contextual loss says that okay, there may be some portions in the image for which the information was not available or it was damaged, but the image which has been generated or the reconstructed by the generator, in that if I take that portion of this generated image which is matching with the undamaged part of your input damaged image, this undamaged part of the input damaged image and the corresponding portion in the generated image, they should match, and that is what gives you the contextual loss. And what you do is you try to minimize both these losses, the perceptual loss and the contextual loss, and while trying to minimize this, go on updating the input vector or the latent vector, and given a latent vector you are getting the generated output. We had done some piece of work on this, where we have done some improvement of the previous work, where what we have done is we have used two type of loss. One is the data loss, which is similar to the loss function which has been used by this previous authors Ye et al., where they have published this work, presented this work in CVPR 2017. This is a recent work that we have presented in ICEEP 2019 in Taipei, where in addition to data loss, we have also introduced another loss component which is the structure loss. And in order to improve the computational complexity, what we have done is we have taken random samples, say 10 samples from your latent space, and for each of these 10 samples, we have generated 10 images using the generated network, and out of these images we have taken that one which is closest to the damaged one, the damaged input image, and the corresponding latent vector z was our initial vector, and we updated on this. So, using both of this, we have found that computationally our method has become much more efficient, and at the same time the reconstruction, because we have introduced a second loss which is the structure loss, that is in the gradient space. So, introduction of the structure loss also has improved the quality of our inpainted images. So, this shows the output. You find that the images in the leftmost column, these are the damaged images which are fed to the generative adversarial network. The three images in the middle column, these are the outputs generated as reported by Ye et al. In their CVPR 2017 paper, and the rightmost column is the output that we have obtained, and this has been, as we have said, that this particular work has been presented at International Conference on Image Processing 2019 at Taipei. The same concept we have extended for video inpainting. So, in case of video inpainting, because as you know that video is nothing but a sequence of frames played at a particular frame rate. So, what we have done is we have grouped those frames into something called group of frames, and we have tried to do the inpainting for every group of frame. So, for that we had the first group of the frame, first frame of every group was inpainted using the same concept as we have applied in case of images, and that particular z vector that you get, that is applied to for inpainting of all the frames in the same group. And if I take say a frame z t minus 1, an initial vector z t minus 1 for a frame t minus 1, finally, whatever the final vector we get at convergence, that becomes the initial vector for the next frame. And using this also, we have observed that our computations is much more efficient than if we use frame by frame as proposed by A et al. Of course, A et al. Did not propose it for the video, they proposed their technique for the images. So, what we have done is we have used their technique for different frames in the video. And this particular set of video sequence tells you what are the computations that we have obtained. So, on the leftmost one, the video samples, these are the damaged video sequence. In the middle, as we said, that what is obtained using the approach of A et al. And the right two columns, the right two video sequences are what we obtained using our technique. And you find that apparently the output that has been given by our approach using this GAN based approach for unsupervised semantic inpainting, this appears to give better result than what you get using A et al. So, with this we come to the end of today's lecture, and in fact to the end of this particular course on deep learning. I hope you have enjoyed the course and you have been able to learn the different methods of deep learning, their applications, their optimization techniques. Of course, we have started our course with the conventional machine learning techniques, where the feature extraction is manual, and then you use the machine learning techniques for feature classification or the data classification. And then we have moved on to deep learning, where even the feature extraction part has been made part of your machine learning approach. And we have talked about different types of networks, the deep neural networks for deep learning applications, for machine learning applications, and this variational autoencoder or the generative adversarial network, which are used for generation of the data or reconstruction of the data or synthesis of the data. This is these approaches are actually the recent trends in deep learning domain. So, I hope you have enjoyed this course, and the course was really useful for you. Thank you.